All right, so this is the second part of this short course on the introduction to density functional theory. This is part 2, and I hope that you have enjoyed part 1 before this one. This is part of a lecture that was recorded for the summer school on computational physics and funded by the NSF at RPI in 2021. So what we did in the previous part, we laid out the fundamental theorems and background for using density functional theory. The first thing we did is to establish the Hornberg-Kohn theorem, which said that basically provide a mapping, a one-to-one correspondence between the density of charge and the property of a ground state of a many-body problem. We insisted on the fact that it's a big deal because a many-body system the wave function has many variables, 3 times the number of particles, plus even the spin that we did not talk too much about, while the density has just 3 variables. So it makes a big difference. Now, what we also learned from the second Hornberg-Kohn theorem is the true ground state density is the one that minimizes the energy functional. So that gives us kind of a way to see which density a particular system described by a Hamiltonian will assume at equilibrium. But what Hornberg-Kohn theorems do not do is to provide a method, an approach, a recipe to solve these equations. And that part is actually provided by the Kohn-Sham equations. And the idea behind the Kohn-Sham equations is to create a fictitious system of non-interacting particles, which is built in such a way that the external potential that acts on those non-interacting particles is chosen such that the density, the charge density of that problem is the same as the charge density of the actual problem. And this is a big deal because we know how to solve the non-interacting particles. And so all we have to do is focus on the things that correspond to the non-interacting particle. And all that is embodied in what's called the exchange correlation functional. This is where we put our finger on the problem with DFT. DFT is an exact theory. So there is no theoretical assumption aside from the Born-Oppenheimer approximation, where we separate the electron degrees of freedom and the ionic degrees of freedom, something we can do because of the huge difference in masses. But DFT itself is not an approximation, but the approximation comes into the fact we do not know what the exchange correlation functional is. So a big piece of using DFT is to try to understand what the exchange correlation functional is. But it's also very, very good to remember what it's supposed to address. And the thing that it addresses is, for example, the Pauli principle, which essentially establishes that if you take the many-body wave function of a fermionic system, if you swap 2 particles, 2 fermions, you do change the sign of the wave function. Of course, it's pretty clear that it's difficult to impose that if you know the density, since you no longer have a handle on the individual electron. So this is something that you hope exchange correlation will take into account. One thing that is always important to remember is that the first approximation for the electron-electron interaction, so the Coulombic interaction, is the Hartree potential. The Hartree potential essentially treats the charges classically. And one big problem with this is that there is a self-interacting potential. So it's very easy to see from the equations, if you remember part 1, that even if you had one single electron, the Hartree potential would actually calculate an interaction between the density and itself, which of course is not correct. So you would hope that the exchange correlation functional would address this by counterbalancing this incorrect interaction. So this is called the self-interaction correction. It's a very important one. And finally, we discuss briefly the correlation effect. So the fact that the presence of an electron affects the properties of the other electrons can be modeled through the correlation hole. So the correlation rule is essentially saying that if you have an electron at a given place, the probability of finding an electron close by must be reduced due to the repulsion between the electrons, which have the same sign. So this is what we did in part 1. Now what I'd like to do in part 2, what I'd like to do in this lecture, is to focus on the exchange correlation functional. And so I can say that it's the art of doing DFT is to understand the exchange correlation functional. So on this image here, we do see kind of a picture of a few functionals. We are going to discuss a few of them, but there are many functionals out there. Most of the time, the functional are called by their by acronyms that are the first letter of the author of the functionals. With of course some exception. For example, LDA is the local density approximation. GGA is the generalized gradient approximation. I'm going to discuss all this in this lecture. So the first thing I'd like to talk about is the simplest functional, and the one that has been described early on in DFT. It's called the LDA. It's the simplest approximation, and the LDA is called the local density approximation. So let's see what it means. It really means that when we calculate the expectation values using the density, we assume that all the interactions are due, all the interaction at a given point are due to the density at the same point. That's what the local density approximation is. In other words, it means that we are essentially treating the system as an homogeneous electron gas. So we suppose that the density is the same everywhere when we calculate those exchange correlation functional. So we are going to see the success of this very crude approximation and why this approximation is good, the reason why it's so good. So just to remind you a little bit of an important equation that we see in the first part of this series. We know how to solve exactly the first three parts in this equation, and the one that's in red, highlighted in red, is the one that we want to work on. So the local density of approximation is the simplest approximation to the exchange correlation functional. And the idea, as I just mentioned, is that we suppose that the exchange correlation functional is the one for a homogeneous electron gas. So what we are stating here, we say, okay, fine, we have to solve Cohen-Sham equations. We know how to solve for the kinetic energy of the independent electrons, the Hartree potential and the external potential. We know how to solve that exactly, numerically exactly. Now, the exchange correlation functional, we are going to say that this interaction between electrons is going to be the same as if the system was homogeneous. This is the first approximation. Okay? And you may think, well, this first approximation is of historical interest, and probably we are doing much better. We are doing much better now, but it turns out that LDA is still used today because it's actually surprisingly, at first sight, surprisingly accurate. So what's very interesting about LDA, as we call it, local density approximation, is that we know we can calculate the exchange term for the homogeneous electron gas exactly. We can calculate that exactly. I actually already showed you this equation in the previous part when I mentioned that the exchange energy tends to stabilize your system. It's a negative sign, just because it makes the electron be of the same spin to be farther away due to the exchange. So therefore, reducing the repulsion since they are farther away. So the other piece is the correlation part. So remember, we separate the exchange correlation functional as an exchange part and a correlation part. This is an example. So the correlation comes from the correction from the fact that we do not have non-interacting particles. And so we can actually calculate the correlation energy of the homogeneous electron gas, and it's going to look like this equation here. The point remains, though, that the EC, so the lowercase EC, has to be calculated using different approximations. So people have been calculating this for years using accurate or exact methods, and one of them is the Monte Carlo, quantum Monte Carlo approach, which like from Sepperli and Adler, which is one of the most popular approach to calculating this. So basically what happens is that it was calculated and parameterized very accurately more than 40 years ago, and this is still what is used for LDA. So we have these things, this seemingly very simple description of exchange correlation in LDA. And then we know that it's an approximation. We know that most systems do not have a homogeneous electron gas description, but we find that it's very reassuring that these results are exact for the homogeneous electron gas. So this is just to before I move on to listing the pros and cons of LDA, I like to show you this plot here, which is always a very interesting plot, which is the ISO surface, ISO density surface for a specific example, zinc selenide. And we compare here between the experiment and DFT. And at first sight, you can see that there is a pretty good match between DFT and zinc selenide, showing that in this particular case of LDA that we are looking at, things seems pretty good. So that should kind of give you a hint that we are probably on the right path. So the success of LDA, you would think at first sight that given the crude approximation we are making, the success should be limited. But it turns out it's not the case. LDA has been very successful. So we know that the exchange correlation potential comes from the exact solution of the electron gas. LDA works very well, even when systems that are far from being homogeneous. And the fundamental reason why it works so well is a purely theoretical one. The reason for this is that the solution for LDA is an exact solution for the specific case of homogeneous electron gas. So what happens theoretically is that when you have a theory coming from differential equations, but coming from any theory that's kind of nonlinear equations, you always have a number of constraints that are due to the theory itself. Okay, so that means that, for example, sum rules, or normalization rules, or rules on the gradients, or whatever, different types of rules, mathematical rules that come inherently from the equation. Since LDA is an exact solution for a simple problem, but still an exact solution, it automatically fulfills many of the rules that I didn't discuss here, but that are known for DFT, especially for the exchange correlation hole. So the sum rule, I mean the equilibrium, the counterbalancing. And it turns out that LDA is not great for correlation. And LDA is not great for exchange at all. However, the mistake that's made for exchange is most often counterbalanced by the mistake we do for correlation. And this cancellation of errors is not luck. You know, sometimes we say, oh, it's fortuitous cancellation of errors. It's not luck. It's because the solution to LDA is, at the limit of homogeneous electron gas, a correct solution, therefore meeting all the sum rules that we have. So LDA works very well, sometimes for the wrong reason, but it also has a number of drawbacks. For example, LDA tends to overbind. So the lattice constant and bond lengths are usually too short. Cohesive energy are too large. Another thing is that the electrons are not localized enough, which is not very surprising since it was developed for a homogeneous electron gas. So in many cases, and I'm going to show that in the next slide with a picture, when we have an S, or we have a system with a majority of S and P electrons, that's okay because S and P electrons are more homogeneous, if you will, in the orbitals. But when we have D and F orbitals, like in transition metals, for example, this start to become a problem. And so when we have localized orbitals like D and F, LDA is pretty poor. LDA does not have any long-range effect, and again, not surprisingly, since it's a purely local one, so only consider the local properties of the problem. So everything that has to do with image effect, so so the interaction, for example, between absorbates and a metallic substrate, or van der Waals bonds, which is purely non-local interaction, dipole-dipole interaction, and I'm going to discuss in a few minutes. These are completely missing. And I'd like to insist that they are missing completely, not just wrongly described. So that means that you may find results that look like, for example, DA does well with van der Waals, but it actually does not. It's not included at all. And I'll come back to that on the long section that I have prepared for the van der Waals interaction in this particular presentation. And also the hydrogen bond is also missing because again it's non-local non-local effect. So one thing I'd like to do is to discuss a little bit these orbitals. This is a typical pictures that many of you have seen. So going from S orbital, P, D, and F, and we see the degeneracies there, the 2l+1 degeneracy, right? We see that it turns out that LDA is actually fairly good for S and P orbitals. But when you have localized orbitals like D's and F's, LDA start to break down completely. So very often we call systems that are strongly correlated, which have those D's and F orbitals, and in that case LDA is poor, and we have to use something else. So historically, LDA has been very successful for a number of cases, in particular for solids. Solids like metallic substrate, or as I'm going to show you in a second, like silicon. And the reason why we have this is because, for example, for metal, the approximation of homogeneous electron gas is actually pretty good. So these things have worked very well, and a lot of things in solid-state physics have been based on LDA in the early days at least. Chemists took a much longer time to adopt DFT. And one of the reasons for this is because of the issues that LDA is certainly ill-suited to describe molecules, which clearly a molecule in a box is far from homogeneous electron gas. So the error that we make, so as I said, overbinding of LDA, made chemists very wary to use LDA. In fact, I can say quite confidently that you rarely see a chemist using LDA in any published result. In fact, even the next approximation, GGA, is not much used by chemists either. And the reason for this is because the LDA is not designed to work well with molecules, for example. So this is an example here of what gives you a good result. For example, in silicon. Silicon can be described very well with LDA, but it turns out it works. The result that we find is surprisingly good compared to experiment. But the reason why it works so well is because the exchange correlation functional is not very good for the exchange part, it's too low, and is not very good for the correlation part, it's too high, but the combination of both gives something very accurate. And again, the reason why it is accurate is because since LDA is a solution that's of the homogeneous electron gas, it fulfills a number of rules imposed by the theory. So one particular problem with LDA is the bandgap problem. We know the bandgap is this energy that you need to excite an electron from a valence band and conduction band. And the bandgap has been a particularly problematic issue because people wanted to use DFT to predict new material for electronics, for logic gates, ever since the first transistors was developed experimentally in 1948. The issue is that LDA underestimate the bandgap. Now, what I like to say, and this is something that's always important to remember, when we talk about bandgap in LDA or DFT in general, we're always talking about this the energy gap between the highest occupied cone charm orbital and the lowest unoccupied cone charm orbital. So I like to insist on the fact that cone charm orbitals do not have a physical meaning. They come from a fictitious problem of trying to map a non-interacting system with an interacting one. Now, of course, there is also theorems that says that the lowest lying orbitals, so that this interaction can be actually be used to calculate transitions. But the point is that the practitioners usually use this distance between the highest occupied molecular orbital, so HOMO, to the lowest unoccupied molecular orbital, the LUMO, as the band gap in DFT in general. So this plot here is a very interesting plot. It's a plot of the experimental gap as a function of the calculated gap, or the other way around. The point is that this kind of plot is always good when you plot it with the same scale on the x and y axis, and a perfect match would have all the data lying on the bisector of the plot. And here you see the LDA result are shown with the cyan color, the square, and you see you are systematically below. Now, you can say that you can imagine in the early days of LDA that if you plotted something like this, you would actually be fairly happy because the trends are pretty good, right? The trends going from all those compounds that are shown in this plot is pretty good. Yes, it is underestimated. That's true. They're underestimated, but the trend was good. But now, of course, as the methods improved and as we were able to do better, we realized that this huge underestimation started to be a particularly large challenge for LDA. I also like to attract your attention that for the number of the first few compounds that we have on this plot, you have to realize that the calculated band gap there is negatives, as opposed to being finite. So you have a number of systems, and germanium is a particular one, where LDA predicted a negative band gap, in other words, a metal, while experimentally there is a band gap. Germanium is a semiconductor. Silicon, which is of course the main material that's used for devices, electronic devices, with a huge economy worldwide, the band gap is grossly underestimated in LDA. So even though we can start to understand a little bit how properties work out, we also, and DFT is not bad at describing silicon, but numerically the match is not great, and certainly not for prediction. So LDA started to be is a very interesting approximation to start to understand what we are doing, but clearly there are drawbacks to LDA. So let's go back to this equation that we've been working with since the beginning. So we are still trying to fix this red box. So what happened is that people have been working, of course, on exchange correlation function for many years, and we like this figure here on the right hand side, which is the Jacob's ladder. So how you go from the Hartree world. So what I call the Hartree world is the world where there is no correlation. So we basically no correlation, no exchange, in fact. So basically, we essentially has no exchange correlation function, and we want to go to chemical accuracy. So the first rung of this ladder is the LDA, I just discussed it. And the next rung is called the GGA, the generalized gradient approximation. And this is something that's best described in the yellow box on this slide, where the exchange correlation now depends not just on the local density, but also on its variation, so on its gradient. And that's what we call, for people doing functional theory, it's a semi-local. So it takes into account the local density, but also its changes through the gradient, through the modulus of the gradient. So that's called GGA, Generalized Gradient Approximation. I'm going to discuss that a little bit more in a second. The rung number 3 is meta-GGA. And meta-GGA start to involve a higher order derivative, but also the kinetic energy, which is embodied by this sum over the square of the gradient of the cone charm orbitals. And then you can go beyond that, hyper GGA, that includes all those things as well, that I described before, but also an exact exchange. And the exact exchange can be done for hybrid GGA, which I also going to discuss in a minute. So we can keep going up and improving this. In fact, there are more and more exchange correlation functions. There are dozens of exchange correlation functionals available. And the recent development, which I will not discuss in this presentation, are exchange correlation functional that are built using machine learning. So trying to describe those functional from a very large database of functionals and try to define a new function that will essentially be transferable to new materials. So this is still a very active field, and I'm just going to spend a few minutes describing a few examples of GGA, and then after that I will move beyond those functional and to look at how we can do completely non-local functional to describe specific cases like van der Waals interaction. So here is an example of what GGA does. So you can see that compared to LDA, GGA is able to have a better representation of the lattice constant in solid, like sodium chloride, aluminum, and so on and so forth, but also the cohesive energy. The cohesive energy of the system is here related on the right-hand side, and we see that GGA, so this particular flavor of GGA, PW91, is able to get a much better energy. And so the improvement over LDA is typical. I mean, it's typical for GGA to improve over LDA because the functional form of the exchange correlation includes a term that depends on the gradient of the density of the modulus of the gradient of the density. So one thing that's important to realize as a student is that there is no such thing as a GGA flavors. So as it turns out that this functional is not the solution necessarily of an exact problem as opposed to LDA. LDA is a solution to the exact problem of a homogeneous electron gas. For GGA, it's not quite the case. So there are many different flavors. Here are just a few of them that are well known: Purdue-Wang, Beck-Purdue, Li-Yang-Par, Purdue-Wang, Purdue-Burke-Erzenhoff, and revised PBE, and many others. So one of the most popular one in physics, at least, is the PBE one. So the Purdue, Burke, and Erzenhoff 1996. It's one that's used a lot. You see those names there that are famous names in DFT. I mean, all of them. In fact, somebody like Purdue is in many of those papers. Becky is more from the quantum chemist side, and Burke and Erzenhoff. We see those people a lot. We are going to talk about another functional later, like HSE, where Erzenhoff is also involved. It's a hybrid functional. So one thing there are mainly two schools of thought. The first one is to parameterize the GGA functional using databases of known results, mostly chemical database. So that would be more like the LIP approach, for example. And so these would actually get functionals that it's almost like a machine learning, if you will, of the old days. The other school of thought, that's one that comes mostly from the Purdue school of thought, is to use exact theorems and sum rules known from DFT, so from a purely theoretical standpoint. And by doing this, build those constraints into the functionals. And this is how the PBE functional has been built. And this is the success comes from both approaches are very successful. You would think that depending on the system what you want to use, for solid state and materials, you would probably want to use something like a PBE if you want to use a GGA. If you're looking at quantum chemistry, you would use something different. In fact, something based on the LYP, but you would actually not use GGA, as I'm going to explain in a second. So GGA is an improvement certainly over LDA, but there are still a number of problems that GGA does not resolve. One of the main notable issue is this self-interaction problem that I mentioned a number of times, that is still not fixed in GGA. So an electron interacts with itself, which is certainly incorrect, and that leads to an issue over the many properties that are affected by this. In both cases, LDA and GGA, the band gap are underestimated. I already mentioned that for the LDA, but GGA does not do much better. And something that has been a particularly challenging problem in the recent years, as we've tried to use DFT in biological systems, but also in layered materials, where van der Waals interaction is important. So one big issue is that the van der Waals description is very poor. In fact, it's even inexistent in LDA, and pretty badly represented in GGA, because van der Waals interaction is a totally non-local effect. So we will discuss also in a few minutes that LDA seems to be working in some instance for van der Waals, but it's purely coincidental from the cancellation of errors, because LDA does not include anything about van der Waals interaction, for example. And actually GGA usually fails completely describing van der Waals. In fact, very often GGA is repulsive for van der Waals instead of have a local minimum. We'll discuss that in more details. So there are advanced approaches, of course, to take into account the self-interaction corrections. Here in the little cartoon I showed there, as you see, the electron sees itself in DFT. It sees itself in PBE, it sees itself in co-charm DFT, but it doesn't see itself in Monte Carlo, like it says. So you see the electron can barely see itself. So this is a cartoonish description of the issue with self-interaction. Something sometimes interesting to remember, to show it. So one thing that people have done also to try to improve the exchange correlation function is to go to the next rung from the Jacob's ladder I showed you a few minutes ago. And one of them is to concentrate on the exchange part. You know, the exchange part, the fact that your wave function is supposed to be, the many-body wave function is supposed to be anti-symmetric upon the swapping of the exchange of two electrons, something that it's hard to impose on the density. And so people came up with this idea of the hybrid functionals. And the idea is borrowed from the Hartree-Fock, so from the Fock part, the fact that the solution there is built on orbitals, on Slater determinant, to make sure that they are indeed anti-symmetric. So here, the way things are done is that the Slater determinants, if you will, are built based on the cone-charm orbitals that we have. And again, remember, the cone-charm orbitals are not physical solutions. They are a solution of a fictitious problem. And so what happens here is that the hybrid functional, the hybrid comes from the fact that you're using both DFT and Hartree-Fock. If exchange was completely absent from GGA or LDA, things would be great, because you would just add the exact exchange. Now the problem is there is some exchange already built in the GGA or LDA, and so that means that you cannot simply afford to add the exact exchange that you calculate from the Slater determinant of the cone-charm orbitals. Instead, you have to mix. You have to add some GGA. So you see this equation here is basically describing this, that the exchange correlation functional for hybrid functional will have the correlation from GGA, but will have some exchange from GGA and some exchange from the exact, remember, built from the cone-charm orbitals. So these are examples, the examples that are very well known in the field, and there are other examples, but these are well known in the field. B3 lip, which is Becky for B, and lip, which is from the GGA I already described. PBE0, which is the PBE plus exact exchange, and HSE, so Heitz, Kuziria, and Erzenhoff. Those functionals are very well known. It's typical for quantum chemists to use B3 lip. These are functionals that have been parameterized using large database. basis of result, of experimental results, mostly on molecules. PB0 again is following this Purdue school of thought, where you impose those constraints, those theoretical constraints, and so you would typically see solid state physicists using PBE0 or HSE, while a chemist would use B3-lip. And B3-lip is actually pretty accurate in terms of bond length and cohesive energy, certainly a strong improvement compared to GGA. So hybrid functional, you can say that when you talk about hybrid functional, you are no longer doing DFT per se, because you are borrowing result from Hartree-Fock theory. So the question, of course, when you do the hybrid functional, is to know if you can start to mix things around. So people have been trying to mix things about and see if we could do some exchange from LDA, some exchange from GGA, some correlation from one or the other, and kind of mixing it up. Of course, here you start to overfit. You start to get more and more adjustable parameters, so things work maybe numerically. Now, one major issue with this is that if you are trying to understand a phenomenon, a quantum mechanical phenomenon, you might be fooled to think that your approach is correct because it gives the right numbers, but it could give you the right numbers for the wrong reasons. So maybe you get the right long bond length, right band gap possibly, but it turns out that you do not actually get, the physics is not correctly described. So you have to be very careful about this approach of overfitting, and in fact it's a problem. I mentioned machine learning a minute ago, but it's a problem of machine learning in general. If you have enough parameters, you can basically reproduce anything you want. That doesn't mean that the underlying reasons for those parameters are rooted in physical intuition. So one thing that I like to show you, one of the success of hybrid functional is this one, which is called HSE. So I'd like you to not worry too much about the TPSS here, but you see in this plot that this is a plot I already showed you before. It's a similar plot I showed you before, where you put the band gap, or experimental band gap, versus a theoretical one, and hopefully you are on the bisector. If a data point falls on the bisector, you have a perfect match. And here you could see that for functional like HSE, which a hybrid functional, you basically fall completely on the bisector for the hybrid functional. We see again the LDA and PBA are both underestimating the band gap, as I already mentioned before. I like just to say a word, because here the label is LSDA. The S is for the spin, so this is local density approximation taking into account the spin. I made the conscious decision not to discuss too much the spin in this series of 2 lectures, but these things can be expanded to the spin degrees of freedom when you are talking about a magnetic system or open shell system. So the hybrid works well, and as I said, there are 2 issues with the hybrid. Is first of all, it's numerically pretty expensive, even though the HSE is actually pretty tractable. Expensive because you have to calculate Slater determinant from the Cohen-Sham orbital, but also conceptually. My main beef is that you may get result that's correct, but maybe not for the right physical reasons. And so that means that you are under the impression that you're describing the physics well, but you might not be able to do so. Granted, very often you are describing the physics well, but it is not guaranteed. So that puts a question mark onto the predictive power of this approach. So you have to be careful about this. Now, what I'm going to talk about now a little bit is more about for the final part of this presentation, is talk about the corrections to DFT, and in fact, those corrections to DFT have been, you could say to some extent that it's no longer DFT. You're doing DFT and you are adding something to it that's not in the theory of DFT. But again, this is all related to the fact that we cannot describe the exchange correlation functional exactly. So three things that I'm going to talk about briefly for the remainder of this presentation are strong correlations, quasiparticles, and van der Waals interaction. And I spend most of the time on van der Waals interaction. So we always like this. This is a famous cartoon. It's very interesting. The difference between particles, like the real particle and the real horse, and a quasi-particle is basically a dressed particle due to the presence of the other one. And this one basically shows that the particles, like the horse and maybe the electrons or the ball or whatever, I don't know what's represented there, both of them are modified by the presence of the other. So the reality is that the quasi-particles is what you should really look at, is a quasi-particle. Now, the strong correlation problem is seen in those systems with d and f electrons, as I mentioned before. And one of the things that's well known is that we have an issue between occupied and occupied band. That the bands are just too close. In fact, in this case, in the case that I'm showing this in this high temperature superconductor, we see that the band gap is completely wrong. So in that case, we actually add a very strong on-site Coulomb repulsion, which is called the U term. And that U term allows to push up the unoccupied state and down the occupied state. So this is something that works when you have a spin system. This is how the U works. And these orbitals are shifted. So the effect the effect of this strong correlation here for LDA plus U is again adding a parameters to allow to separate the occupied and occupied state, and you hope that you are able to represent the physics this way. This is again, the U parameters can be calculated with a higher order theories, but usually it's empirical parameters that is adjusted so as to represent the physics. So this is a very typical thing that people do when they look at strongly correlated material. Now, people who want to do to look at the band gap, as I mentioned to you, HSE or PB0 or B3LIP has the band gap pretty well, but it is for those systems where the exchange part is the most important one. But I'd like to talk about this quasi-particle thing, the fact that the electron and hole basically are dressed by the presence of the other. And so this transition between electron and hole, which is giving the band gap, we have to screen essentially the carriers. And this is something that's done very often in GW approximation. So the GW approximation is a Green's function approach with propagators, and it's using a certain number of Feynman diagram in the many-body system. It is not a DFT approach, really. The reason why we usually talk about GW on top of DFT is because it's using DFT as the zero-order solution of GW. So what you would do a DFT calculation, and if you need to understand the correlation, you want to represent the screened particles, so quasi-particle, you would actually perform a GW on top of DFTs. It's fairly typical. And again, you see on this plot that GW does the job. And in this case, the GW approximation is really rooted on very firm theoretical considerations, and therefore we understand why things are correct and not. It's not just a matter of overfitting sometime. So the last thing I want to talk about is the van der Waals interaction and how we treat that in DFT. The past few years have seen the explosion of those layered materials in material science. Started with graphene, and then we had the transition material, the dichalcogenide, and all sort of other system with van der Waals interaction started to play a big role. On top of that, we also would like eventually to be able to use DFT in life sciences, where van der Waals interaction is very important. So it's very good. It's very good to remember what van der Waals interaction are. So the van der Waals interaction is really, at least there are different type of forces, van der Waals forces, but one important one is the London force, which is between a dipole, between induced dipoles. So I found this little animation on the bottom right that I'm going to play in a second, which shows the dynamics of two particles that interact, that have initially a dipole that's actually aligned in two different directions. So that's what the dot shows. It shows the direction of the dipole. And so as you play this, and I'm going to play it now, as you play this, things are starting to move until they're actually going to move in phase eventually, because they try to minimize the energy, so to maximize the interaction between the particle. And this is what you end up going. And it's related to this induced dipole. And this induced dipole comes from this induced, so it comes from a non-local effect. So a charge density that feels a dipole moment of another particle. So clearly from the description of the non-locality, you do not expect LDA or GGA to be good at describing van der Waals interaction. And yet van der Waals interaction are very important to describing biological material, but also those weakly bonded material. So this is an example I always like to show my student. Is like if you look at the molecule of life, DNA, and if you look at the structure on the top, which is what you would expect to have, so a helical and a ladder structure between the individual bases. If you were to do this, if you were to describe that structure without DFT, with DFT, but without any van der Waals corrections, you would see that you would completely lose. You would lose the structure of DNA. You would lose the helical symmetry. You would lose the ladder structure. So basically, you would not be able to represent a biological compound, and I would even say go as far as that you wouldn't be able to represent life or use DFT in life science. So that's one example. So let's try to have a look a little bit about the long-range forces that we can describe. So for many times, people, for the longest time, people didn't believe DFT could be extended for long-range forces. And the reason why it was like this is because people were pretty happy with LDA and GGA and kind of didn't discuss the long-range interaction simply because it corresponds to non-local correlation from the induced dipole interaction. And it was really understood that that was really something that could not be done. Well, there is something worse to this, is that if you use an LDA calculation, which, by the way, van der Waals interaction is completely absent from an LDA calculation. And if you calculate the energy as a function of the distance between two subsystems, you might actually reproduce something that looks like a van der Waals interaction, like a 612 Lennard-Jones type potential. You may very well see something like this. And so it makes some people say, people who don't know any better, I would say, makes them say that the van der Waals interaction is represented by LDA. This is a wrong statement. It's completely incorrect. The reason why LDA is able to represent this is because it overbinds, as I explained before for LDA. So it overbinds, it corresponds to more binding than it should. And on top of that, because of the cancellation of errors, things work out as if it was representing the non-local interaction well, but it does not. It just numerically gives something that looks correct from cancellation of errors that I already mentioned before. So please do me a favor, if you ever do DFT calculation on where van der Waals interactions are important, and you realize that you use LDA that gives the best result compared to experiment, it's okay to say that for cancellation of errors you represent the interaction well, even though you understand that LDA should in principle be incapable to represent non-local interaction. But say that, do not say we use LDA because it works well for van der Waals. This statement is obviously not appropriate. Now, you can go further than this and say, what about PBE? Well, PBE, as you know, or GGA, PBE is an example, B-trip is another example. These functionals are semi-local. They include the gradient of the density. And so they are incapable to represent non-local interaction either. And in fact, if you look at the interaction between this noble gas, like krypton, like krypton in this example, like between two hexane on the right-hand side, you would expect the interaction to be mostly of van der Waals type, of pi-pi stacking, of that sort. Definitely non-covalent, non-binding. And then you see that in each case, compared to the reference between a couple cluster, which is basically a higher order quantum chemistry result, the GGA interaction is very poor. In fact, in the case of the stacking between the two hexanes molecules on the right-hand side, you see that there is no local minimum. In fact, PBE would, or B3LIP even more so, predicts that those two molecules will actually separate. The minimum energy is at infinity, which is of course not correct experimentally. So that's an issue. By the way, if you were to calculate this same calculation with LDA, you would find a local minimum, and as I explained 5 minutes ago, that would be for the wrong reason. So the correction must be brought to conventional exchange correlation functionals. The reason I like you to remember is because van der Waals interaction are purely non-local effect, and non-local effect are the hardest one to describe. Okay, so basically non-local means that the interaction at a given point depends on the density of every other points. That's what non-locality means. And so people came up with a number of schemes, and here I'm just going to show you one approach that people have used. It's come from this paper from Michailidis from 2012, where there are also a ladder, like the Jacob's ladder I showed you for the functional, where there is also a Jacob ladders for the van der Waals interaction, and then a number of ways to correct your exchange correlation functional, or at least your interactions to interact to get things correctly. So I'm just going to talk about 3 of those rungs, the 1, 2, and 3. The first one is the most obvious one, is that you add an energy term. So the attractive term that's usually missing, and we usually do that on top of GGA. So the attractive term, the C6 over R6 term, is simply added by hand. So this is something by pairwise additive, so it's between 2 atoms I and J, and the coefficient C6 is chosen so as to represent the experiment. So this one is actually pretty straightforward. It's basically a classical approach, an empirical approach, I should say, to describe the attraction that's missing from GGA. So if you do that, you also have approaches that use a damped correction. So if the attraction is actually too strong, you can have a damping factor, damping function f, until you find something that looks about right. So again, this is parameters. We are trying to adjust the parameters. So we are far away from our goal of ab initio here, as I discussed in the previous part of this course, where I explained that ab initio we would only base our result on the constant of nature. Here we are really getting dangerously far from there, since we have more and more parameters we want to work with. So there are other approaches, like for example DFT plus D2. This is jargon that's used, and this one is extremely popular from Grimy, where the C6 is obtained from a geometric average of the C6 of 2 individual atoms, and where we use a static polarizability, so we go back into the fundamental origin of the van der Waals interaction. You can also go beyond that. You can do what's called DFT D3 or DFT TS for Tchachenko and Scheffler. Those approaches calculate C6 with different hybridization states. And these work pretty well. Many cases work pretty well. But again, there are coefficients in there. But what I always tell students is that if you're studying a problem where van der Waals is important, you should probably look at kind of benchmark the different approaches to see which one gives the more accurate result. I mean, it's accurate is always compared to experiment, but also the most logical result. So you cannot just say one approach beats all of the others. So you have to start to try that. Now, these are all corrections, if you want, kind of empirical corrections, almost like a heuristics. But there are also other approaches. The other approaches that really are about changing the exchange correlation functional. So to add a non-local part to the exchange correlation. And so you see here the example of a non-local functional on the second row of this slide. You see typically that the energy depends on the density at 2 points, and R prime. And so you integrate over everything with phi R prime being the kernel that you use to get the correlation from the non-local part to address the van der Waals interaction. So these become very computationally challenging. These are difficult, but these are based on fundamental physics, so it's more theoretical and more closer to ab initio, if you will, because it's using fewer parameters and fewer fitting function. So these are usually called on the rung number 3. So is our Jacob ladder for van der Waals interactions called van der Waals DF. So there are different there are different methods. Some of them are called from the Longrange approach, which is the van der Waals DF itself, and also the one that are called OPT 88B. There are different OPT that exist out there. These are, I find that in many cases in layered material, the OPT series work pretty well. Again, this is from an intellectual standpoint maybe quite attractive to use a non-local functional instead of a C6 like Grimy and so on. But it turns out that there is no such thing as one solution fits all. So this is again very interesting. But what is very exciting about all this is that van der Waals interactions start to be very well described, and improvements come all the time. So just to give you an idea of what's happening, here's just a table I want to show you. This is how you calculate those van der Waals correlation functional. So the first 2 rows, of course, are just our good friend LDA PBE. So this, with the first one being local, second one being semi-local. So semi-local is when the functional only involves the gradient. And then after that, you start to have a number of other functionals like the DF, the DF2. Some you also have D3 on top of PBE and so on and so forth. There are plenty of them. In fact, the number of this is becoming very, very complicated. It looks almost like a library of terms that are becoming harder and harder to follow. But the reality is that there are plenty of functionals out there. And in fact, this is just from a paper from 2013. There are more and more functionals. And the best approach is to try them and to read the literature and to understand what kind of class of functionals work best for a given problem. So I'd just like to show you some examples of the success of all this. And here we have a molecular solid, it's a solid methane. So it's basically methane on a lattice, if you will. And then you see what we see here is how things are going. Compared to for different functional, what we get compared to experiment, which is marked by the red vertical red line, and then we see that when we have this PBE or PBE0 or B3 lip, which they're both hybrid, and we add van der Waals interaction of the type Tchachenko, Schaeffer, or Grimy, we see that we are very close to experiment. That's what I wanted to show there. And so we get the cohesive energy is strongly there is overbinding of LDA, as we can see. We can also have overbinding in a number of PBE as well, underbinding in terms of PBE as well. So these are results that should be able to understand what's going on. And you understand here, of course, the importance of van der Waals interaction in methane, since the individual methane molecule do not create, of course, ionic or covalent bond with their neighbors. It's all pure non-local interaction. So the next slide is a bit busy. Sorry about that, but this is for this complex between noble gases like argon and krypton. Here, if you want to look at this more carefully, I suggest that you pause the YouTube video, but you will see that one thing that you will see that the different functional give different results. That some of them not being very convincing. One thing I really like to insist is the LDA, which are the crosses, is the black crosses on both cases, and you see that LDA, even though it does not include van der Waals at all, as I already mentioned, it provides a very nice and deep local minimum for completely wrong reasons, and it's because there is an overbinding. On the other hand, you can see that PBE barely binds, so there is an underbinding of PBE, as I also mentioned, and so essentially the van der Waals interaction, the correct one, is something in between. So here we have a lot of data. These are benchmarking, very useful benchmarking to understand the effect of the different functionals. This is here another example when we have a hydrogen molecule on copper 111. I like this result a lot because it's very clear. Those authors have looked at different functionals, and you see the experiment in the black curve, and you can see that the van der Waals, the DF2, so that the red line gets very close to the experiment. And again, PBE does not have a local minimum, or a very shallow one. Ref PB does not have a local minimum. On the other hand, you see that you have some overbinding in some van der Waals approach. I did not, these authors did not include the LDA corrections in this one. So this is what I wanted to discuss in this presentation, which for a total about 3 hours or maybe 2 hours and a half. So I had to make choices. I understand that I was not able to cover everything in DFT. I also decided not to discuss about codes, how to use software. The main reason why I didn't want to do that is because I believe that most of the softwares that are released today, most of them being open source, are excellent software with excellent tutorial and excellent guide. But I also strongly believe that before you embark into following a tutorial on DFT or any other code, actually, you should understand what you're doing. So I believe that understanding the fundamentals, principle and equation and where things come from is actually essential in order to be able to understand the data that you get. One thing that's always funny about DFT is that you can get beautiful images even though they are wrong. So you can create wonderful density plot, wonderful images, and they might be completely wrong because they are not interpreted the right way. So there are more and more packages developed by physicists and chemists and engineers. And one thing that I did not discuss at all is how we represent those data. Actually, I discussed a bit about grid as an example at the very beginning of lecture one. Physicists like to use plane wave. Chemists like to use Gaussian-like basis or like LCAO basis. Other people have been developing wavelets, multi-resolution approaches. But they are all relying on the use of supercomputers. And the packages are robust, and you can actually find benchmarking about the different code compared to one another in recent papers. So that's very useful. I personally can tell you what are my favorite ones and the one that I usually use in my group, and feel free to contact me in the comments section, and I will let you know what I believe about this. So DFT has been excellent because of the theoretical development, but also because of the computational development. So the computational development have allowed people to look at systems with thousands of atoms now, and the quality of DFT should be accompanied with the training of students who will use DFT to interpret the data. I would even go as far as saying as these presentations here, those two talks, were really geared as much towards the experimentalists as theoretician in order to really realize what we are doing with DFT these days. So in my closing words is that more and more people use DFT packages. There are plenty of reviews out there, and there are plenty of fundamental insight that can be obtained. There are a number of books that have been published recently. I actually recommend the 2 books there that I show you on the right-hand side on this slide. There are also very good review papers, which tend to be a little bit more concise. But those 2 books, the first one in particular is a book that's a little bit more entry level, I would say, even though it's excellent. And the second one is just after entry level, and it's also excellent. And I strongly recommend them to you. Please do not be tempted to use a code blindly. It's not because you get a number that it is correct or you understand it. If you are a material scientist, a chemist, or a physicist, remember that's what you are. You are not just running code like you are playing a game. You are running code because you are trying to understand the fundamental science and the underlying principles that guide the science that you are interested in. I'd like to thank you very much for listening to these 2 talks. Do not hesitate to send me your remark. If there are mistakes that you have noticed, let me know and I will fix them. And thank you very much.